me go full screen. And it's 5.2. Okay. Uh, so I reconnect with yesterday. It wasn't, I mean, depending on how much you drank yesterday night, you may already have forgotten what I said. So DADAM is this singular corner of our body of knowledge of active matter, where alignment is the only, local alignment is the only interaction, competing with noise, given self-propulsion. And we work, although this has not been really important so far, in some dilute, what I call the dilute limit. It's also because particles are pointwise, so they do not have a physical size, so there's no repulsion. So then really it's, you can think of a dilute limit. But that I'll come back to this later. So there were three classes that you can define within the what I would call the Vicek straight jacket, where polarity is velocity and velocity is polarity, and none of the realistic features that Olivier just discussed happen. Of course, that's not realistic, except in some cases. And these three classes are here, and they depend on the nature of a motion of particles, which can be just polar motion without velocity reversal. Okay. Apolar motion, meaning some motion with a finite velocity reversal rate. So you just, you know, and the symmetry of the alignment, which can be ferromagnetic alignment, okay, the sum of vectors, or nematic alignment, which basically at the level of pairwise interactions means anti-alignment for obtuse angle. Okay. Now, polar ferromagnetic, that's a Vicek model, and we saw that there's a general scenario where in this you had a coexistence phase between the disordered gas and the ordered liquid. This coexistence phase is made actually of a smectic of polar traveling bands, okay, in the Vicek case. In the nematic classes here, because the nematic alignment gives rise to nematic global nematic order, the coexistence phase is made of nematic bands. So these are very different. The particles travel along them. So the order is along the band. These bands do not move in a propagative manner. They move around due to fluctuations and instabilities. And in fact, they are something I haven't shown yet, but I've said, I'll show today, they are actually chaotic regimes where, because the band solution is itself linearly unstable generically. Okay, so these are the three classes. Now, it's a reasonably clear picture, I hope I gave you at the microscopic level. And now we turn to continuous descriptions. And my aim here is, I would say, of course, only or mostly qualitatively faithful theories or descriptions, continuous descriptions. You know, given that I start from a silly, unrealistic starting point, I don't see really any point of aiming at quantitative agreement, especially at this stage of our knowledge. I'm quite happy, and I'm actually quite happy to have been able to found hydrodynamic theories in a systematic manner that do account qualitatively for all that are, almost all are presented today. At the fluctuating level, some work remains to be done, as I will argue at the end. But basically, the aim here is to get some qualitatively faithful continuous descriptions, including the phase diagrams, what happens in the coexistence phase, and all these things. Okay, so yes, how to go from particle models to continuous theories. So we've heard some of this today, actually, and already also Mike Shelley did some of this in the context of swimmers. You can also dispense with all this, and because you are very well educated and believe in gradient expansions and work in well-ordered settings where variations are assumed to be small scale, small and long wavelength and long time scales, etc. You can write down equations for the conserved or hydrodynamically relevant fields. So the Vicek model Toner and 2 in 95 did this as a starting point for their calculation. The paper is not derivation of the equation. The equation is just written down just like this. So the density is conserved and vectored by velocity field. This velocity field is the one that is assumed to vary slowly in space and time, with in some kind of gradient expansions where you allow yourself a certain number of possible gradients and maybe a certain number of V fields. And if you look carefully, it's most of it's at least 2 V's, 1 grad, like in the Navier-Stokes advection term here, but you can also, this one and this other one there, which has 3 V's, by the way, are also allowed because you do not have, I mean, you write down all the terms that are allowed by the symmetries of the system. And in this case, there are very few symmetries or conservation laws. Okay. Then you put here some positive alpha, which will be compensated by this negative term or cubic term, giving rise to a finite on average velocity or speed, the Ginzburg-Landau kind of feature. It's a compressible system, so you have some pressure. You have here some anisotropic pressure, and here some anisotropic diffusion terms, plus some ad hoc noise, because what Toner and 2 did is some RG calculation, basically for a stochastic fluctuating hydrodynamic equation. So if you would like to have more terms, you're welcome, especially if you say, okay, maybe this one has 2 V's and 2 grads, maybe I can add more terms. You can indeed add more terms, and you would see that in the RG sense they are all irrelevant, so there's no point of writing them down. But it's not quite true that this is all the terms you could write at this order in number of V's and number of grads, but it doesn't matter. Okay, now here you already have many terms. Okay, 1, 2, 3, 4, 5, 6, many coefficients. These coefficients, because it is a compressible system, a priori depend on the local density rho and V squared. So they're functions. And of course here, most of them are assumed to be constants with the proper sign, you know, assume that beta is positive, and this really saturates the linear instability that you have here, and so on and so on. So basically you have a complicated problem with unknown coefficients, some of them actually functions of the density, and it's very important for this one in particular to be a function of a density. This is what gives the instability of a ordered solution, giving rise to the coexistence region. And you have lost, of course, or maybe you're not interested at all, in the connection between these many transport coefficients and the original parameters of some microscopic simulation or some microscopic experiment where you have some things that you can vary in your experiment. Okay, you have to interpret or guess which of these parameters you would like to vary to mimic what's happening when you do this or that in your experiment. Because in your experiment, you know, you do not have a lambda 2 that you can, lambda 2 button doesn't exist. Okay, so that's one way of doing things. And of course, from my viewpoint, because I want to show you that you can arrive at hydrodynamic theories that are faithful to at least some microscopic models, that's not a way to go, because I have lost already here all connections with microscopic parameters, which in the Vic-Check case are just 2 of them, basically. Okay, so the good news is that there are systematic approaches which may start from a microscopic model and will derive hydrodynamic equations. In the Vic-Check case, will derive a Toner 2 equation. Okay, they're more or less sophisticated. Some names have been actually, it's missing here and Skog. But anyway, you can do Fokker-Planck-Stage, Smoluchowski, Boltzmann, Chapman and Skog, all these fancy names. Kinetic theory is a rather messy subject. We prefer Boltzmann, and I will say why, without showing exactly all my reasons for my argument. But basically all this starts with a kinetic one-body equation. So it's a kinetic equation governing the evolution of a one-body PDF like this, f of r and theta and time, which rules the probability of finding particles at position r with orientation theta at time t. Okay. Already, so strong assumptions come into being able to write a self-consistent equation for just f, as Olivier just mentioned. Okay, but basically all these methods, you don't need, I will not explain to you the differences much. I will show you mostly Boltzmann. All these methods rely, first rely on writing down a kinetic equation. Now, work at the kinetic level can be done numerically and analytically to some extent. We've done some of this recently for these 3 basic classes, and lots of surprises were found. And I will not dwell into this, but it's typically hard, you know, and now you will see why very clearly in a moment. Now, what is next, what is done usually once you obtained through very drastic approximations in this context, you obtain your kinetic equation governing f. Usually what we do and what most people would do is actually an expansion of this f in terms of Fourier modes of the angular variable. That's one way of doing it, but that's the one we prefer. Now, if you develop f into these Fourier modes, inject in your whatever kinetic equation, what you have is a hierarchy of PDEs for fields, which are these Fourier components of f. Then you have an infinite hierarchy. You haven't done anything. You see infinitely many PDEs instead of a kinetic equation. So far, you didn't lose anything. And comes another hard problem, how to truncate and close this infinite hierarchy so that it's actually a simple set of PDEs, hopefully doing the right thing. So that's the program. That's the program for most people in this business. Okay, now, here you have to believe me, and that's a little bit for specialists, but anyway, and the Boltzmann approach assumes a dilute limit, so hence DADAM is pretty good for this. Dilute limit means in this context that particles only interact by pairs. Okay. The Fokker-Planck-Smoluchowski is some kind of opposite limit where you assume that you have many, many, many particles locally, and any given particle feels the mean field of these many, many other particles nearby. So it's a sort of a large number of neighbors limit. The Chapman-Enskog approach, which has only been performed mostly by Thomas Ehler in this context, is much more complicated and is able to deal with multiple collisions. But all these still rely on this molecular chaos hypothesis that Olivier mentioned, which is a very strong, typically unjustified approximation. Molecular chaos, let me say it now, assumes that in between 2 collision events or interaction events, you lose memory of the previous one. Okay. Now, if the interaction, the collision, results in alignment, so particles come into each other, they align, they move away, but they move away together. So a priori, this molecular assumption, chaos assumption, is a very bad idea for alignment. And it is. Okay. Now, whatever you do, hopefully at the end, especially in the simple cases, well, the one-body kinetic equation you obtain once you've done whatever you've done here and applied molecular chaos so as to have an equation for just f of r, theta, and t. They all look the same formally. Now, in practice, to arrive here, it's much easier to derive then hydrodynamic equations, which means expanding in these Fourier modes and truncate and close, amounts to a total amount of work, which is typically, it's easier for Fokker-Planck-Smoluchowski than Boltzmann. Boltzmann itself being much easier than Chapman-Enskog. So here, I will stay with Boltzmann because of things that I will not show you much, because by experience, we find that the Boltzmann Ginsburg-Landau, we call it approach, which allows to truncate and close systematically in some nice controlled manner, gives better results at all kinds of levels. But I will mention them here and there. So that's my viewpoint on this. We can discuss this privately later if you want. So, where is this? I'm going backward. No, that's no good. Okay, so what I will do here, and I will insist on, is there is something that I was educated with in nonlinear dynamics, which is weakly nonlinear analysis leading to amplitude equations, so-called Ginsburg-Landau equations. And that's here being to be applied as a closure scheme. So I will not sit a priori, so I do all these very strong assumptions to have this kinetic equation. Then I go into the Fourier modes of a theta angular variable. That's an infinite hierarchy of PDEs for these fields, and I need to truncate and close. Yeah, so how do I do this? You can stay deep in the ordered phase and do the kind of closures that Olivier mentioned a bit. Or you can sit near the onset of order, assuming that the heretofore isotropic angular distribution has small modulations, and these Fourier modes in the angular variables will be hierarchically separated from each other. And that's what we use basically to have a scaling ansatz which allows to truncate and close. So you'll see this now in more mathematical terms, but that's what we're going to do. Quantitative agreement is completely out of reach, given that the assumptions we're making, even at the very initial stage, are clearly bad. Nevertheless, pretty much as in nonlinear dynamics, where you derive these amplitude equations near the onset of some instability, and then, of course, when you do an experiment, you are never infinitesimally small close to the onset of the instability, and you observe that the amplitude equations remain valid, at least in some semi-quantitative, qualitative level, even very far away from the onset of this instability or the onset of order. So here we proceed, because we know by experience that the Ginsburg-Landau closure provides typically equations which are well-behaved, do not explode, have well-behaved solutions, which is already something in this field. Okay? So let's do it. So the Boltzmann equation, for those of you who have done some of this kinetic theory for ideal gases, it looks like this. You have this one-body distribution F of R and theta. Some forces may be applied on the system, self-diffusion under some fluctuation, some noise here, and collision terms between the particles of a gas. So here there's no external force, but there is a self-propulsion which replaces the force term here, which basically means that you move at speed v0 along your current orientation theta according to the gradient of f. It's a classic advection term in this kinetic context. Now the angular diffusion integral accounts for, it's basically some kind of, yes? Yeah. Two particles align, they stay together, they self-diffuse away from each other. But typically, if you are at some finite density, it's very likely that they are going to experience other collisions before the self-diffusion has killed completely the memory of their current nearby orientations. And then at the next collision, they are correlated. Well, here you assume molecular chaos, whatever, and you have global alignment arising. No, it's not. That's not really. Probably the truth is that they're slightly decorrelated at the next collision, of course, but not totally decorrelated. So we make this jump to totally decorrelated only for practical reasons. Otherwise, you have to deal with, two-body distribution functions, but then to close, you need to factorize the three-body or four-body, whatever, which is something that Thomas Hiller has been working on, making things even more complicated. And this is always justified if and only if you're really interested in quantitative agreement with something, you know. And I'm not. It's not my goal. Yes. Well, apart from the work by Hiller, nobody has looked at this seriously, aiming at quantitative agreement with something. So here it's really the most basic stuff. My goal is to arrive at the Turner-2 equation, okay, in some systematic way that provides the transport coefficients as a function of the microscopic parameters, and check varying the microscopic parameters, and all these transport coefficients then vary, that the phase diagram of the PDE has the same features as the microscopic model. Qualitative agreement, that's it. Now, if you want to be serious, of course, you have all the problems, the usual problems, even for ideal gas in kinetic theory, plus many other problems due to the active and alignment interaction and so on. So really, yeah. Okay, so here, so this Boltzmann equation is really like a master equation, what comes in, what comes out, you know. The probability of here, so self-diffusion, you have here at some rate lambda minus f, which means, okay, at some rate, I will deviate from my current orientation, so I go away from theta, so I have to count them, it's a minus f. And here it's a plus at the same rate. It's particles which did not have orientation theta before, but at the previous time steps, if you do it in discrete time. But now have the desired orientation theta. So you have to average over this theta prime over the noise. And here's a delta function which fixes that theta prime plus the noise, which does this self-diffusion, gives you theta. It's really a master equation in some sense. All right? There's a lambda is so P, because it's some angular variable, usually you can choose whatever you like, but P remains formally the noise distribution, typically unimodal, centered around 0. Okay? Now, the collision integral, so particles are sparse and they only interact by pairs. So you have typically to have to deal with a probability distribution function of having a particle, two particles at more or less the same position R with orientations theta 1 and theta 2 at the time t. And you factorize this as a function, as using the one-body probability, and that's a molecular chaos thing. If you write the probability of having two particles, etc., and you don't know how to deal with it, you need an equation for it, which involves a three-body probability and so on, or four-body probabilities. So you factorize a priori, and then what you have is this: a collision integral for having two particles colliding is again. So here you have the collision kernel, which is a geometric factor depending on, everything depends, this k and this psi depend on the type of motion, on the alignment, or interaction type. That's the kernel k that Olivier mentioned before, okay? That's how you lose, you know, particles. Here is a minus g, because they are going away from this orientation theta 1, theta 2. Here is the true collision term here, where you work out the probabilities of having two particles coming with some angle theta 1 and theta 2 submitted to some noise psi, etc. And here's the factorization of a probability distribution function. And here this function, the delta here sets how the two particles we end up with position with angular direction theta, given that they had theta 1 and theta 2. That's the alignment. So with roughly here for ferromagnetic alignment, this would be the half sum of these two angles, plus the noise. It's always acting also in the Vic-Check model. You put noise also on the collision events of it. When the particle is alone, it has no neighbors. It only feels the noise. When particle has neighbors, you align. I mean, you calculate the local averaging, you align, and then you add noise also. So there's always noise, and this noises in particular, in principle, should be different here and in the self-diffusion equation, but basically here we assume to be the same. Doesn't matter so much. And basically, so here you have your alignment. That's all the interaction is in here. It could be more complicated than just a half sum. We can discuss this later. And the nature of a motion is this geometric factor, classic in kinetic theory, that comes into this kernel undefined here. And I will not give you the explicit expressions for this. I can give you a reference where all this is done in too much detail, in a lot of detail, any detail you would like. Okay, so basically, the physics is in here. It's in these two functions. Everything else is very, very standard for particles moving. Yes. Yes, yes. Yeah, here it's just to distinguish. We actually it's f and f, but f of theta 1 and f of theta 2. So for clarity, yeah, there's only f. G and h are other names given to f for clarity here. So this, you know, you put all this together in this thing. You have self-contained evolution equation for this one body, which is an integral differential equation, if you want. Okay, looks complicated. Most of these calculations can be semi-automated on Mathematica or something also, or the integrals in particular. It's always the same integral, so they're very simple to do. They involve integrals of trigonometric functions mostly, so not too hard. Depending on what you choose here, basically, of course. Okay. So this has remained very general. You can do this in all cases, and the k and the psi functions make all the difference in the symmetries. Once you have this equation for f, you can put it in a computer. One way of doing it, putting it in a computer, is actually to expand f expand theta in Fourier modes, and you have now fk's like this, which are fields. Okay. The f0 field, if you look at it, is just the density field. The f1 field, here it's so I'm working in 2D. In 2D, the Fourier expansion of this single angular variable is quite nice. If you're in 3D, you would have to do spherical harmonics and things like that, which is messy. We've done this recently, but okay, that most of what I say is in 2D here for calculations at least. So f1, which is a complex field with a real part and imaginary part, is actually a vector, a polarity vector. It's actually rho times the polarity, the local density times the polarity field. So the equation would be that I will arrive at will be for f1 in the polar case. This will not be a velocity field. It will be an equation for rho v, not v. Okay. Anyway, that's a detail. The second mode, f2, which is a complex field also, you can construct a traceless tensor from this f2 field, and this traceless tensor is rho q, where q is a nematic ordering field, and so on if you go further. So you can give special names to f0, f1, and f2, but I won't. What else is interesting? To write the Boltzmann equation in Fourier in terms of these Fourier fields, it's convenient also to introduce these complex gradients. Stay in this complex notation, and everything is really simple to deal with. Here's the Boltzmann equation in some generic case actually here, where you see that fk is coupled by advection to fk minus 1, fk plus 1. You have a noise, the self-diffusion part is here and over there, and the collision part actually is hidden in these factors. These coefficients here. So this is a calculation that you can do once in your life, and then basically it's always the same afterwards. These coefficients are actually including the k, and here, sorry, the psi has become an h. but basically the alignment interaction is in here. The kernel is the same kernel. Delta is the difference between the two incoming angles, like in Olivier's notation, I think. And here, the noise distribution has been also expanded in Fourier modes. So here is this hierarchy of equations, infinite hierarchy of equations for coupled complex fields. This is totally equivalent to the Boltzmann equation. And numerically, you could just simulate this. It's hard, but it's doable, and we've done some of this recently. Of course, because it's infinite, you need to just consider a large number of these modes and truncate, close arbitrarily at the large modes, and it's in most regimes, it is doable to do numerical simulations at this level. Nevertheless, mathematically speaking, this is complicated. So the problem now is to reduce this infinite hierarchy to an evolution equation typically for the density field, and that's easy, and for the relevant hydrodynamic fields. So which are those? You can study, of course, the Boltzmann equation or any kinetic equation has as a fixed point, as a steady state, the homogeneous isotropic disordered solution corresponding to the gas, where F0 is ρ0, the global density constant in space, and all the Fk's different from 0 are 0. This is a trivial solution of a Boltzmann equation, okay? You can study the linear instability of this solution in the infinite hierarchy. That's not too hard. In fact, you can easily find that these equations, if you look at them at the linear level, the linear terms, involves this coefficient. This is the noise thing. And this is an omega k. It involves some of these quantities, integrals that I described before. So you have df0, df1, df2, and dfk equals this coefficient times f0, f1, etc. These coefficients vary. And you can, these coefficients, and you know them, or this one, for example. Okay, whatever is in front of the linear term, mu k, you have very easily explicit expressions for these mu k's. I mean, you can if you choose the noise distribution and your functions, you can calculate these mu k's analytically. Mathematica will do it for you. And what do you see? If you say treat the nematic case, you will see that only mu2 corresponding to f2, the nematic field, can change sign, varying ρ0 or the noise strength. All the other mu k's, larger than 2, for k larger than 2, will be negative, and all the more negative as you go down, increase k. So you don't even have to guess what is the relevant hydrodynamic field. You can see it from just the inspection of these coefficients. In the polar case, you will see that mu1 can change sign. When mu1 changes sign, f1 grows, polar order grows, etc. And you see that then in this case, f2 is negative, f3 is even more negative, f3 is more negative, etc. So the f2, f3, f4, the large k modes are strongly damped. And that comes out from very simple calculation. So you can know exactly which field is going to emerge, which order is going to emerge, and how strongly slaved the higher order modes will be. Okay, what did I say here? Yeah, so typically in all the three classes we're interested in, only mu1 or mu2 can change sign. Okay, if mu2 is the one changing sign, like in the nematic problems, you have to keep f1. You have to deal with an equation for f2, but you have to keep an equation for f1 in principle, and of course for the density. So you know which fields are the slow fields, and these mu k's can be calculated rather easily. Yes? Yes, but you have to tune some parameters to get there. And in the rods case, so in the nematic, active nematics, if you take the extra assumption that the velocity reversal rate is large, I mean very fast reversals, by constructions all the odd modes will be 0. Okay, and then it's a super simple case, in fact, and nothing of that sort can happen. In the rods case, you have to keep F1. F1 will not be 0 by construction. And you can see that there are some parameter values where maybe, yes, 2, or I mean, in this simple picture could be, but these are typically unphysical parameters from the Vic-Check viewpoint, or happening for values of the fields which are also unphysical. You know, the modulus of F1, for example, cannot be larger than rho 0 on the, at least on the homogeneous solution side. Okay. So all this, what is this? It's the same thing. Okay, down. Next comes the closure thing. So I know which fields are going to be important. The conserved density field, F0, and then whatever F1 or F2, depending on the one that can change sign. Of course, I knew this in advance because I know what's going on in my system. But anyway, it's still good to find it analytically like this, simply. And then I want to keep only these fields, so F0, the density, and F1, or F0, F1, and F2. And then enslave, truncate, and close my hierarchy to have only self-consistent equations for F0, F1, and F2. I know it's a good idea because I know the mu k for k larger than 1 or 2 are very negative, so these modes are quickly damped. Okay, but I do better than this. So that's where the Ginsburg-Landau approach is important. So I will use a small parameter which typically governs how far I am from the onset of order. So if mu1 changes sign, I will work in the vicinity of the mu1 equals 0 region in parameter space. mu1 is the linear coefficient that can change sign if I vary my global density or if I vary my noise strength. So I sit near there, near mu1 equals 0 at some distance epsilon squared from mu1 equals 0 in parameter space. Okay, then classically, because I expect the Ginsburg-Landau approach to work, I will have the ordering field of order epsilon, in a typical pitchfork bifurcation. Okay, for each case, there is a unique, well-defined scaling ansatz, and I'll try to illustrate to you now how it can be done in the active nematics case. Okay, so you assume that you are at distance epsilon square from the mu2 equals 0 point, in this case. You assume that F2 is of order epsilon. Okay, you have a continuity equation, which is the equation for rho, written here in semi-complex notations. This is an exact equation. The first equation for F0, for the density, is an exact equation involving diffusion, but also a non-trivial coupling to the nematic field, which was first found, cleverly guessed by Sriram Ramaswamy, which is at the origin of all the interesting stuff in this system. Here it comes very naturally out of this very simple calculation. And this is an exact equation, so there's no other terms. You notice that all the coefficients, there are no V0s there are no, you can rescale or scale out at the Boltzmann level, at the kinetic level. You can scale out all parameters in this if you start from a Vic-Check model, except the global density and the noise distribution or noise strength. So it is strictly true at the kinetic level and hydro level that you can forget about all the other parameters in your Vic-Check thing. So here, this is exact. I want to balance the terms. So I know that I have assumed that F2 is order epsilon. The gradients must be some power of epsilon. If I want to balance all this, I'll let you do it as an exercise because I don't want to get myself embroiled into this. The conclusion of balancing these three terms exactly is that alpha here must be 1, so the gradients are order epsilon. The partial t is order epsilon squared, as in any diffusive problem. And the fields are order 1, and rho, or rather delta rho, the local deviation from the global density, is also order epsilon. Yes? Yes, yes, yes. That's what you see it also. You can scale it out, and there's no way you can go to equilibrium or whatever you want to define as. So here, um, just in the good cases, I mean, there are some details, but especially in this case, just inspecting seriously the continuity equation, which is exact, and insisting on balancing all of the terms in terms of powers of this small parameter epsilon, gives you the right scaling on that. Then, so mu4 is negative, you can check that, meaning F4 and strongly negative. F4 is enslaved to F2. And if you count dt F4 in the equation for F4, this term is already of high order compared to whatever is on the right-hand side of the equation for F4. And that leaves you immediately to F4 being enslaved to F2, and in fact, F4 can be replaced by F2 squared up to some prefactor that is of course given by the equation. F4 is epsilon 2, then epsilon squared, and indeed you can conclude that the right ansatz is this. Okay, so this is a bit of balancing terms, etc., assuming that the gradient is some power of epsilon, some partial t is some power of epsilon, delta rho is some power of epsilon. If you want to balance, you're forced to conclude this. F2, I have to define epsilon somewhere. F4 is epsilon squared, F6 epsilon cubed, etc. Rho minus rho 0 epsilon, grad epsilon, and partial t epsilon squared. Now you take your hierarchy of dtfk equations, and for each term in this thing, you can assign a power of epsilon to each term. Now partial t f4 will be epsilon 4, right? So far I've done nothing. Then I say, okay, I keep only terms at epsilon cube. It's always cube if you've defined your thing properly. It could be 6 if you have a double. Anyway, the only, if you truncate at order 1, you have nothing. If you got order 2, it doesn't work. The only order of epsilon where you start having self-contained equations, of meaningful self-contained equations, is order 3, and you stop there. So basically, all the terms have some power of epsilon. I kill everything that's larger than epsilon cube. What's left? Okay, so the higher order equations is basically 0 equals 0, because everything is of order higher than 3. And for the F4 equation, you have 0 equals F4, which is order epsilon squared, plus, I forgot the coefficients, of course, here, F2 squared. So this is epsilon squared, this is epsilon squared. This one I have to keep, but that gives me F4 as a function of F2. Okay? That's a classic Ginzburg-Landau thing. Now if I reinject, so the equation for F6 is 0 equals 0, so I just forget everything. So I just have to inject in my F2 equation, which contains only F0, F2, and F4, this expression of F4 as a function of F2 squared. Then I have closed equations for, I have an exact rho 0, F0 rho equation, continuity equation, and I have a closed equation for F2. And that, in all cases, works in the sense that it gives well-behaved coupled nonlinear PDEs with the right nonlinearities. And in all the cases that we're talking about today, so if I inject F4 in the equation for F2 as F4 is F2 squared, more or less, it's basically in the F2 equation I have an F2 F4 term. This term becomes an F2 cube firm. The coefficient better be of a correct sign to saturate the linear instability of F2. And you can see by these calculations that in all the cases I mentioned here, it's always the case. All these linear instabilities are saturated by the cubic terms, which do have the right sign, whatever you do with, as a function of the Vic-Check original coefficients. If I write arbitrarily my Turner 2 equation, the beta term in the Turner 2 equation, they assume it's positive. It's minus beta V cubed. Okay, here I calculate that it is positive beta, or the term is minus something, minus cube, whatever I do choose to do with my Vic-Check original parameters. No, I'm not assuming. I see it. No, sorry, I did not assume it. I told you, you look at the mu case, the linear coefficients, at the kinetic level, okay, you see that only one, at least for the cases I'm talking about here, only one can change sign. All the others basically are strongly negative. So I know which mode I have to deal with. Okay, so I didn't choose it, I didn't assume it. Now I do this systematic procedure, and I find always, in the cases I mentioned here, that the cubic term has the right sign. No, the variations around rho zero are long wavelength and slow and so on. That's conserved field. No, I did not use that rho zero. It's more formally for the Boltzmann, to arrive at the Boltzmann equation. Yeah. Or the Fokker-Planck, actually, it's the same thing. You know, you can start with Fokker-Planck if you prefer. We can discuss in private why Fokker-Planck is not as good, although it's easier to do. It looks easier to do. In fact, if you're getting used to these Boltzmann integrals, it's always the same calculation. So you do it once in your life, and then you keep some notes. Right. So, but I did not assume. I calculate, and I want to insist here. You know, you've heard Olivier and Shelley to some extent telling you, I don't know. And here, you know, it's a systematic thing. You can be dumb, and Mathematica will help you, and you'll find the right thing, guaranteed. Now, more complicated problems, microscopic problems, okay, we can discuss, but it is in these simple cases, it's. Yeah, sure. Hmm. So the cubic term will depend. The cubic term will depend on this. In front of the coefficient, there is some integral involving your interaction function, psi or h or whatever it was. Okay. Now, if you choose something more complicated or whatever different than Vic-Check, there's no guarantee, but you can calculate it. That's the good news, you know. And if it doesn't work, you can proceed to truncate at the next meaningful order, which is typically epsilon 5. But then, by experience, there's no guarantee that the equations you get are actually well behaved. But anyway, so far in the cases I'm treating here, it's not happening. Everything is fine and dandy, almost. Okay, so now, how does it look like? So here, for the nematic case, focus on the right-hand side. It used to be a pointer, but okay, doesn't matter. I'm close enough. That's the exact continuity equation, okay, with this fancy nonlinear current term that Sriram Ramaswamy guessed a long time ago now. Here you recognize the linear mu2, loss is 2, sorry, okay, minus the cubic term. So in complex notations, it really looks like an amplitude equation, okay? And the psi has been calculated to be safely positive, whatever you do with your Vic-Check parameters, okay? Plus diffusion, that comes out, also the calculation, plus a coupling to the rho field, of course. And that coupling is a square of this complex gradient is not diffusion, okay? This is corresponding, if you want in the polar case, this is the pressure. In the pressure term, if you calculate in the polar case, the Turner 2 equation is just grad rho. Here, this is this tensorial thing. So here it is. It is a real complex, a real Ginzburg-Landau equation, if I forget about this, coupled, interestingly, in the simplest possible way, to a density field which diffuses, but is also coupled, interestingly, to the ordering field. And the coefficients here, because I've rescaled everything I could to 1, are some simple numbers everywhere except mu and psi. So I have an explicit expression for mu2, which I showed to you already, and for psi as well. Oh, here they are. Sorry. Here they are as a function of the local field rho. Mu depends, in fact, on the local rho. Okay. When I do the linear stability analysis at the kinetic level, I found mu2 as a function of rho 0, but in fact, it's a function of local rho. You have the term that you had before. If the noise becomes large, this will dominate, and mu will be negative. If noise is small, this might become positive. If rho is locally large, mu can be locally positive. And here you have a feedback between order and density that I keep telling about coming out of this calculation. And the fact that mu as a function of rho is an increasing function of rho is the reason why you have a coexistence phase. And now let me go to this now. Psi, believe me, is positive. It looks like it could be positive. It depends on what is this, but anyway, it's safely positive. Nu is this thing which depends on rho and the noise and so on. It's just to show you that you can do this calculation. It gives these ugly looking things which you might want to simplify later, but at least you have something to start with. That's systematic. Yes? Yes, sure. Yeah. Yes. Yes, yes, yes. But what you need, whatever you do, you will find, if you do something correct here, you will find some messy which is increasing with rho. That's key. And it's always, and for the models we're thinking about, it's always mu prime is positive. And now, so what happens here? So when mu is negative, okay, the only solution, global attractor of this set of PDEs is rho equals rho 0 everywhere, F2 equals 0, disordered solution. When mu becomes positive, F2 can grow, saturated by the cubic term, and you have, if I forget about the gradients, if I do the especially homogeneous analysis that Olivier has started doing, I balance these two terms, so I have an ordered solution of modulus F2 squared equals mu of xi, okay, which goes from 0 continuously in typical pitchfork bifurcation, or mean field continuous equation. Okay, now, this exact solution at the hydrodynamic level, which is F2 equals mu of xi and rho equals rho 0, spatially homogeneous ordered solution that exists. You can study its linear stability. It's easy to do. You go to Fourier space and you study the full linear stability of this exact ordered solution, and you will find that near mu2 or mu equals 0, in the side where the solution exists, and you study its stability, this solution is actually unstable to long wavelengths along the order, okay, because mu prime d mu over d rho is positive. You see it. Okay, here the connection between the fundamental feedback mechanism between order and density, which makes so that near the onset of this mean field onset of order, the solution, especially low amplitude homogeneous order solution that emerge, is actually linearly unstable generically, whatever you do again, if you vary your Vic-check or whatever parameters. Well, that one depends. This is an instability of the ordered solution. So in the Vic-check case, it's a longitudinal mode that comes in. In the nematic case, it's a transverse mode that dominates. And all this comes out of fairly simple calculation. You can do it analytically in the small q limit. You can do it semi-analytically for any q perturbation of your solution, solving 3 by 3 matrices. It's not too hard. I mean, your computer will do it for you. Then you have a full phase diagram, which I will show in a minute. Okay, did I say everything that I had here? Probably yes. Yes. Okay. And what do you have? You have two Vic-Check parameters, the noise amplitude, that's the variance of this P of a Xi distribution here, and the global density rho. And typically you will find two lines at the linear level. So the black line is, if we stay in the nematic case, which I described, is where mu2 or mu1 in the polar case is 0. Okay, so that's the linear onset of order. Below the black line, I just told you that the emerging homogeneous ordered solution is linearly unstable generically, provided mu prime is positive. And it is unstable, linearly unstable, until this dotted purple line. So in all this, this is for the nematic case. It's actually a real diagram for the nematic case. In this small region here between the black and the purple dotted line, there are no homogeneous solutions to the PDEs. The disordered solution is unstable, the ordered solution is unstable, something else must happen, and what happens is bands. Now, these bands, we'll come to this in the second part of this talk, hopefully, if I get to that. These bands, in fact, you can observe them. They exist and they are stable. Well, they exist. Stable, we'll come back to this later. They exist not only here, because something must exist here, maybe some chaotic solution, but made of well-defined solution like bands, in this case, in the nematic case. But they also exist and are observed until the yellow line and down to the red line. So these two lines mark the region of existence and stability, to some sense, observation window of an inhomogeneous solutions to the PDEs. Now, in a fluctuating system where you would put back fluctuations, what you would observe in your Vic-Check, what you observe in your Vic-Check model, so to speak, is this as the onset of order, this as the end of the coexistence region, where you had the bands, etc. And here the liquid. So the liquid is below the red line, the gas is above the yellow line. Between yellow and red, this is the coexistence phase. These are the binodals, and these linear thresholds, given by linear instability of homogeneous solutions, are the spinodal lines. Yes? Yes. So there are in the Vic-Check case that I'll show this in more detail later. Yes, indeed. Yeah, it's a choice. If you choose to separate the two noises, for example, if only that, but anyway, but it's a systematic thing. You get this, and this is the liquid gas picture coming out of this. Actually, very simple calculations up to here. This involves analysis of the nonlinear inhomogeneous solutions. I will come back to later. Okay, what do I have here? Probably I said most of this. Yes. So for an experimentalist or in numerics with fluctuations, these linear instability thresholds are not the thresholds you observe in your system. There's been some. Okay. All right. I think I said most of this. Now, so far this was mostly about, although I touched the yellow and the red line, was mostly about the linear homogeneous solution and their linear stability. Now we're going to discuss the inhomogeneous solutions of the three cases, basically two, because the third one is the same, so it doesn't matter. Starting with active nematics. It's good because I showed you the equation. Here it is again. The exact continuity equation with this famous gradient current here, and the F2 Ginzburg-Landau self-contained equation like this. Now, if you like tensorial notations, you can, maybe you prefer to read this with this thing being the Frobenius operator and whatever, but myself in 2D, given my education, the complex field notation is so much more understandable. Now, in 3D, this is wrong. In 3D, generically, you will have a quadratic term here. And that comes out if you do the hard work of dealing with spherical harmonics and all that. Of course, it's well known. If you open Pro and Dejeune book on liquid crystals, you'll find the term. But okay, now, in this 2D system, 2D and actinematic simple PDEs, you can find numerically the band solution being stable in some largish domain in your simulating the PDE. Um, here are the almost the same colors as before, except that this is not red and this is not yellow. But basically, you find these are the two linear stability lines of the delimiting the instability region of the ordered solution. And these are the regions of existence, limits of existence of a single band solution, single band solution. And here you have very small band covering zero of the system, and here you have a band covering almost all of the system. So it's really like phase separation in the nematic case. If you are in a if you do small simulations of your PD in a smallish domain, you'll find a single band. It will stay there nicely, and this band will occupy a fraction, a growing fraction of the system as you go from here to here. What fixes the width of the band is some, well, the global density and so on. There is actually, it's a connection of two tangent profiles, and you can find, if you insist on connecting them in closed form, you'll find that the solution is a cosh like this. And here, hidden in there is what sets the width. It's a complicated balance between the global density. So here is a case, a nice case, where this band solution, we know its form in closed form, explicit closed form, as a function again of all the parameters we need. Yes? Yes. Of course. But that, what the hell? I also assume that the molecular chaos is fine, you know, which is probably worse, in fact. No, really, I proceed. What I claim here, and I hope to convince you, is that whatever I arrive at is mathematically well-behaved, smooth, well-behaved solutions, and qualitatively does the job, because we know from experience, and it can be made more precise, but if you even in, you know, classic nonlinear dynamics amplitude equation settings, as long as no other symmetry breaking or major event happens in your system, the framework given by your Ginzburg lambda up, you know, of course the coefficients will go wrong. If you have a secondary instability, of course, things will be different, and so on and so on. Yes. Yes. No, no, but really the philosophy here, I've made worse assumptions on the way, you know. I insist, in particular. Yeah. Of course. But you find the right row dependencies and which, you know. Of, I mean, which parameters? You're doing the PD parameters, the microscopic parameters. Starting from my starting point, making the assumptions I'm making, it is always of the right sign. That's all I'm saying. On the way, I made very bad assumptions, very bad. Bad. You know, I can see Trump tweeting about this, you know. Bad. In the end, I still have nominally my microscopic parameters, and I can do whatever I want with them. Instead, take, well, maybe I cannot take the speed to be negative, or, you know, whatever. And it all this is robust. I'm happy. That's my goal, was just something like that. Now, it is true, and in more complicated cases, we can also deal with, for example, a bit of repulsion, so force depending on distance. In this case, you do see that you push it. If you push this approach, you systematically, you crank it, you get very nice results, more complicated equations, but then there is a limit, in particular in the global density and maybe the noise, where everything breaks down. But we're still happy with this because anyway, this limit of very large density of repulsion, it's, it's a jammed, glassy, whatever it is. And so it is really robust, qualitatively or semi-quantitatively. Any amplitude equation business is like this. By experience, people know that their complex Ginzburg-Landau equation is going to work until some new symmetry breaking thing happens. Until then, qualitatively or semi-quantitatively. Actually, you do experiments on pattern-forming systems from experiments which are done far away from the onset of order or instability of pattern. You can estimate the Ginzburg-Landau parameters of the amplitude equation, and then you have a quantitative match between whatever you see in your experimental system. Because nothing else happened. If you have secondary instability coming in, that's it. That's the end of it. So here is to claim that in this very nice, simple case of active pneumatics, we have an explicit expression for the band, which allows to do linear stability analysis. So linear stability analysis of inhomogeneous solutions is actually a hard work, so we actually don't do it. We have a clever collaborator, Igor Aronson, who was also even better educated than me in nonlinear analysis and so on, and is able to detect the presence of a long wavelength instability. So if there is a long wavelength instability in this inhomogeneous solution, some analysis, rather simple that we do, detects it. If there is a finite wavelength instability, it will not be captured by this. Okay, so now we do this on this equation, on this solution for this equation. Here, the width of this thing, the width of the Koch, is given by system size. You can also compose different smaller bands together, etc. But the simple reference single band solution exists. It's like this. And we can prove that it is always linearly unstable to long wavelength. To a long wavelength instability that we do not really know, but we can detect it. So, and it is along the band. So in 1D or quasi 1D boxes, this band solution is very nicely stable. If I have an infinite or very long system along the band, it is indeed unstable. So that's why you end up doing simulations of a PDE in a ridiculously long box, and you indeed see that to check that the calculation was there. And then this instability develops into chaos. And here so these coupled PDEs actually have, in the coexistence region, have a spatial temporally chaotic solution. Yes? Yes, it is the coupling again between density and order at the interface, because in the band it's a flat thing, it's the ordered, in the band it's dense enough and ordered enough that you are in the linearly stable region, okay, locally. Now at the interfaces, of course, it's the only place where something can happen. Yeah. So these very simple looking PDEs, so it gives Ginzburg-Landau coupled in a minimal manner for tensorial field coupled to density, conserved density field, have in this whole region here, in between the yellow and red before, only spatial temporally chaotic regimes in the asymptotic infinite size limit. At finite size, a very nice paper by Robert, which explains to you in detail and very nice that in finite size, and you would argue that any realistic system is finite size, you can actually have a stable band and so on, and very clear analysis. Okay, so but I'm talking about the asymptotic world and Vic-Sheck world, so everything is of relevance zero, so to speak. Haha. Okay, Vic-Sheck for rods. So now I have the polar particles, no velocity reversals, and nematic alignment. Okay, like the little microtubules, etc. This now F2, the nematic field again, mu2. Where is it? Here is the one that can change sign. The non-linearity has the right sign, believe me. But F1 is not zero by construction, and I have to keep it formally. I can notice that in practice it's always much smaller than F2, and I can, in a second, I can try to enslave F1 to F2, and then I'm back to the previous case. it is not clear to us whether you should really keep it or not, given our observations that the long-range order might be true long-range order in this case, in the fluctuating system. We don't know, but maybe the coupling to F1 and all that is structurally important at the fluctuating level. That this is something that, okay, so that's what you get. You more or less have the same. If you enslave F1 again, you back to the previous case. It looks complicated. It has the same sort of structure. The rho field is advected by the F1 field, which is a polarity field, as in the Vic-Shack case, as you will see in a minute. And then all these three fields are coupled in a minimal way. These terms here have the right sign, so they don't cause any trouble. In fact, beta is negative also, minus, yeah. Anyway, they don't cause trouble. There is a solution with F1 and F2 modulus non-zero, but that solution is unphysical because the F2 and F1 values are beyond. But okay. Yeah, so you have the same band solution, because if you look for the band solution, setting F1 to 0, it's also a solution of these three coupled PDEs. You can also do the stability analysis that I mentioned. And the band solution in this setting is also always linearly unstable to long wavelengths. So it's also chaotic coexistence phase. So at the deterministic hydrodynamic level, except from some decoration from this really small F1 field, it's basically the same picture. Okay, now finally Vic-Shack. So polar particles, ferromagnetic. Here are the Tourne-2 equations in their full glory for the Vic-Shack model. So the continuity equation, of course, is there, and it's complex notation for, grad minus grad of rho v. Exact equation for rho, of course. And the equation for the velocity field, or rather the rho v momentum field, if you want. F1 is rho v, is not strictly v or polarity. Is, yes. I think this sign may be wrong. Anyway, doesn't matter. This is a pressure term, which is just grad rho. Here you have a Gibbs-Landau mechanism with mu1 changing sign as a function of parameters. The cubic term with a right sign, positive here. Some diffusion in green. And here the two advective terms written in complex notations. We only have two, and they include the key nonlinearity, Navier-Stokes nonlinearity, of course, of a Tourne-2 equation. The same thing in vectorial notation is really, okay, there's lambda here, this is the lambda 1, and this one is a combination of lambda 2 and lambda 3, the kappa term over there, the two kappa terms. The pressure is here as a simple coefficient because I rescaled everything I could to 1. So it's basically as simple as it could get. You have no anisotropic diffusion here because the Vic-Shack problem has no explicit spatial diffusion. So that's less terms. The pressure is very simple by construction. That's it. This is the simplest, one of the simplest expressions of Tourne-2 equations. And I know lambda, mu, psi, nu, and kappa as a function of the Vic-Shack parameters. Okay? Now I can study, I can study as a function of global density rho 0 and noise strength, the phase diagram. And it will be, like I said before, these four lines. The linear instability at mu equals 0 gives rise to a homogeneous ordered polar solution, everybody moving together, but that's linearly unstable until you're deep enough in the ordered phase. And then in between these two spin-order lines, you only have inhomogeneous solutions. What are they? They are band-like, traveling band trains. I'll show this in a minute. And they exist until some spin-order lines, which are hard to define, but anyway. Okay, so how to find the inhomogeneous solutions here? Yes? Now the equation they write down in all generality. The calculation, they take v equals v0 plus small fluctuations, and the longitudinal ones are slaved, as you mentioned. Yeah, the stability, what they do is the stability with respect to fluctuations of the polar phase, assuming I'm inside it. And they don't even do this because, as you know, they neglect, okay, so as to not be forced to do the calculation. Anyway, how to look, and you mentioned something like this, Olivier, I think so. Now I have these 2D PDEs, toner 2. Now I want to look for solutions that propagate at constant speed c. No, I want the solution first. First step, I want to look at solutions which have some variation along the order. There's everything moving. Okay, I'm looking for solutions which are inhomogeneous along the direction of motion and completely steady, stationary in the other direction. Let's call it y. So now the 2D PDE for a complex field becomes a 1D PDE for a scalar field, M, called M, for historical reasons. 10 minutes. Oh, that's almost good. You will never know about the fourth class, but too bad for you. So the 2D PDE has become, if I do this, I restrict myself to solutions that are homogeneous in Y. My order parameter becomes scalar and everything. So 1D PDE for scalar parameter M here. Okay. So it's the same equations, same different notations. I'm sorry because it comes from a different paper. But now I'll not only are looking for solutions like this, but I want solutions that travel at some fixed speed c, and in this frame, moving at speed c, the solution is stationary. In other words, all the solutions I want to find are functions of z, x minus ct, and only z. If I impose this, my 1D PDE becomes a system of ODEs, ordinary differential equations, okay, where m and rho depend now on z, okay. So that's a dynamical system with, now I can solve this one up to some integration constant, which has to be the gas density, because if m is 0, I have no order, what's left is what's outside the ordered dense region is the sparse gas. So rho g is the gas density. I can solve this one, re-inject rho into this one, and what I'm left with is a single ODE at second order in z, or in time, pseudo time, whatever. So dynamical systems with 2 degrees of freedom, that's manageable. So a full analysis of this you can read about. We look for solutions by shooting methods, mostly, that go from m equals 0 at minus infinity to m equals 0 at plus infinity. Or, so we have two sorts of solutions to this sort of dynamical systems. You have fixed points. These are the homogeneous solutions in the PDE setting. You have periodic solutions. These are wave trains when you translate back into the PDE language. So they are like the trains of bands. And you might have heteroclinic connections, which are basically or homoclinic connections. I go from a fixed point at m equals 0, disorder, I do something and I come back to it. That's a single solitonic-like solution propagating at speed c and so on. You can also have heteroclinic connections connecting the m equals constant homogeneous solution to the m equals 0 homogeneous solution in a front, and couple this to another front, and then you have a single packet moving. So all these solutions exist. They exist in a large domain of a Vic-Check parameter space. If I choose Vic-Check parameters, I still have a 2-parameter family of solutions parameterized, say, by the speed, c, and the gas level, or whatever else you like in the system. That is a 2-parameter family. So at almost every point in parameter space, in the coexistence region at least, I have infinitely many and twice infinitely many existing solutions. Most of them are periodic solutions like this, okay, which propagate in the PDE setting. That's a 2-parameter family, a 1-parameter family of solitary waves, just one connecting at infinity 0 and 0, and a single heteroclinic connection in terms of a domain. Now, again, the linear stability of such solutions in a PDE, when translate them back into the PDE, it's a hard problem to do. You cannot do this analytically. You can do numerically some studies of whether these solutions that you input from the shooting methods giving you the solution, you input this in a PDE as an initial condition, and you look whether this relaxes to something stable or whether this is unstable. It's called numerically assess the linear stability of these inhomogeneous solutions, which are many, many, many. And what you find is that many, many, many of these solutions are linearly stable. Okay? And that's bad news because in the microscopic model, I think I've said this, whatever you do, you always find the same well-defined band, and the same well-defined spacing between these bands at fixed parameter values. Here, what I'm saying to you is that at fixed parameter values, I have infinitely many embarrassingly coexisting and linearly stable solutions. So at this hydrodynamic level, there is no way you can account for the selection of a single band solution. Almost no way. Yes. Yeah, sure. Now what I can tell you is that's recent work. If I keep everything, I do simulations of a kinetic equation, the Boltzmann or Fokker-Planck. Actually, the Boltzmann, because the Fokker-Planck is unstable everywhere, so it's a mess. Same conclusion. So, I mean, from studies, with 10, 20, 40 modes, painful studies, we see, we cannot tell you infinitely many coexisting solutions, but clearly many, many coexisting solutions, linearly stable, at the kinetic level. So, even if I had kept F2, F3, F4, F27, whatever, it would not be enough. Yeah. Yes. Yeah. Yeah, but something else happens. There is a very long and very detailed and very nicely written by Alex Solon, because it's too painful for guys like us to do PRE paper in which all the details of this analysis are given. Does not require much knowledge of dynamical systems, and you can see that in some sort of, I mean, it's a complicated argument. Within the PDE, you can argue that I'm going to find the binodal lines, but these are complete. Now, in practice, so what I'm saying to you now, no, it's not true. And also from this analysis, these results are structurally stable, as we say in dynamical systems word, meaning I can perturb them, unless I perturb them singularly, this is robust. This is robust to keeping into account F2, F3, F4, and even F37, whatever. Yeah, but what is noise? So the kinetic equation, as I told you already, I made horrible, bad assumptions, and that thing, it's an infinite dimensional complicated object, but still does not solve this selection problem. Okay. Now, how to solve a selection problem? You do like Toner and 2. If you're a bit lazy, you put a bit of noise on the equation for F1 for the V field, some simple additive noise or whatever, and immediately your PDE selects a single solution among these many, many coexisting ones at the deterministic level. So I think I will leave you almost there. I mean, maybe yeah, there's a summary. Okay, the summary is what? Okay, we have 3 classes, etc. There's an overall satisfactory situation. I hope you would agree with me. If not, okay. With a qualitative agreement, okay, between micro and hydro level. We have some results that kinetic level which confirm this, actually, which also show that the Fokker-Planck equation is, for example, Fokker-Planck equation gets it the homogeneous ordered solution in the Fokker-Planck equation is everywhere linearly unstable. And the order is not monotonous with, as you go away from the, it has some qualitatively bad features. If you start from Fokker-Planck and do all this work, and with Ginsburg-Lambda on that, you find results with the same hydrodynamic equations, of course, different coefficients. And you see that some things are different, but it's not too bad. So at the hydro level, everybody is more or less safe because it's more or less always the Tonneau 2 terms, and they are not so, the dependence on local things are not too important in this case, at least. Okay, now, nevertheless, there are some pending issues. Most of them are at the fluctuating level. So really the hard work still needs to be done, is to study stochastic PDEs and not hydrodynamic PDEs, preferably with noise terms which have been derived from some kind of calculations. We started doing this instead of putting just some additive noise ad hoc something and hoping, crossing fingers that that is not causing any consequences. Because as you would notice, there is only noise if there are particles in this system. So the noise, at the very least, has to be proportional and multiplicative in the density. And this is known to be able to cause qualitative differences at the fluctuating level. So, for example, whether there's true long-range order in the rods case, with fluctuations, true long-range nematic order is something that, okay, numerically maybe we can go further than what I've shown you, but really RG calculations should be all the scaling exponents, all these things. Most of the pending issues are at the fluctuating level, where you need to do RG or stochastic simulations of the right PDEs or right noise terms. Of course, there's also 3D and so on. And I have no time to talk to you about the fourth class. I will tell you what it is. To have ferromagnetic alignment and apolar motion, which is a case missing here. As I told you, if velocity is polarity, then the reversal of velocities and verse of polarity actually break any possible order. No order can emerge. If you say now I have a polarity and I have velocity reversals, whenever I reverse velocity, I do not reverse polarity, so that polarity is plus or minus velocity always. So that's getting out of this self-imposed Vic-Check framework. Then, to the price of this minimal new development, which goes towards considering separately polarity and velocity like Olivier did, then you can have indeed, if you do this, so you have particles which reverse velocity at some rate, but the polarity, so they move like this, but the polarity which we have does not reverse. And then you align these polarities ferromagnetically, you have emerging long-range, quasi-long-range polar order. The mechanism, the mu prime mechanism, feedback mechanism between local density and local order is not there by construction anymore. You have a continuous transition, no coexistence phase, a critical point, a line of fixed points in the RG, continuously varying exponent in the ordered phase, ending at a true second order phase transition critical point in this case. But you can read about this somewhere in a good journal. Thank you. I can hardly hear you, so. Yes, yes, yes. Yes, yes. That's why we have done this, and indeed you're right. You can also do Boltzmann Aladdin, so to speak. But okay. No, they're not different. The right way of doing or accessing fluctuating stochastic hydro equations would be a Dean approach, but you can do it Boltzmann style which is something we've done actually. We just, haven't done anything with these equations yet, but